Okay, hello everyone, can you hear me? Okay, cool. So welcome to the course Deep Learning Theory and Data Science. So now that we're on YouTube, I have this desire to start every lecture by asking everyone to smash the like button, comment below, subscribe to the channel. Soon we might have merchandise. I'm not sure what kind of merchandise, but if anyone has any suggestions, I would appreciate them. I was thinking of cups or maybe t-shirts, but I'm not sure. It should also be related to the course. So what's the bell? I'm not sure what the bell is. Is the bell the like? It's not the like button, right? Oh, that's the subscription. No? Okay, I'm confused. So I forgot to mention in the first week that my sister is actually a mathematician, and she's also, we are serious. Yes, we're very serious. So yeah, so my sister is actually a mathematician, and she actually follows the class as well. And she watched the previous lecture on YouTube, and she actually scolded me for not explaining properly what a convolution is. So I thought I would spend the first minute of today's class on showing an example, a very concrete example of what a convolution is in the simplest case, just to make sure that we understand what this is, because this is so fundamental in the actual networks people are using, right? So here you can see an example of a convolution between a certain, let's call it a kernel, which is -1, or a filter, there's different names for this, and a certain input signal. Now, you can see that once you convolve a signal with a filter, it becomes slightly shorter, right? So the length of the output is smaller than the length of the input. Sorry for being so crooked. Now, what does a convolution do? It's something very simple. You take a patch of length 2, and you do an inner product with the filter. So once you do an inner product between 1, 1 and -1, 1, you get 0, right? And then you switch to the next neighborhood. So you do an inner product between 1, 1, and again, -1, 1. So what do you get? You get another 0. Then you move to the next neighborhood. So the next neighborhood is 1, 1 again. Oops. It's 1, 1 again. So again, you get an inner product between 1, 1 and -1, 1, and that gives you another 0. Then we have 1, 2. So the inner product of 1, 2 with -1, 1 is equal to 1, right? And afterwards, we have 2, 2. So 2, 2 inner product with -1, 1 gives us a 0. Then another 2, 2, which gives us another 0. Another 2, 2, which gives us, oops, I might be missing a 0 here. And then finally, we have 2, 3, which gives us the 1 again, right? So let me try to depict it. So if you think about the signal is basically 1, 1, 1, 1, and then it jumps to 2, 2. How many 2s do we have? 2, 2, and then it's 3, 3, 3, 3, right? And so if you convolve with this signal, every time the kernel is here or here, right? I guess here, is going to create this 1. Does this make sense? So hopefully this explains what a convolution is doing, and hopefully my sister will be satisfied with this explanation. Yes?
Hi, Professor. So is that true that the dimension of the output is the dimension of the input minus the dimension of the signal?
Minus the dimension of the filter, I think you mean. Yes.
Yes, dimension of the filter, yeah.
Yeah, that is correct. That is correct. Okay, so at this point, we've seen many architectures in the previous lecture, we've seen the multilayer perceptron, we've seen the LeNet, we've seen VGG, we've seen ResNet, we've seen DenseNet, right? So there's a bunch of different architectures. And what we want to do is we want to somehow train the parameters of these architectures over a data set. So in the case of a multilayer perceptron, what are the parameters of the architecture? The parameters of the architecture, which are going to be denoted by theta, are just W1, W2, I guess I should do it like this, W2, etc. And then B1, which is the bias, B2, etc. right? So you can think of vec is an operator that takes the matrix W and just creates a long vector, right? So we have here a long vector of the first weight matrix, a long vector of the second weight matrix, etc. And then we have all the biases, and everything is concatenated to a very long vector, right? Now, once you have this vector, you would like to optimize this vector. You would like to find the optimal parameters. And so what you do is you try to optimize over this vector by minimizing this loss function, right? This is the loss function. So we've seen two examples of loss functions. One was the mean squared error loss, and the second is the cross entropy loss, right? Now, usually it is common to add this L2 squared term to the optimization because empirically it was shown to be better to add such a term. And in statistics, this extra term is called ridge regularization, right? Has many terms, but essentially it's just a small, tiny quantity that you add to the loss. So usually lambda is something like 10 to the minus 4. So lambda is a very small scalar, and you have lambda multiplied by the L2 norm squared of the parameters. Now, notice that the loss function that you're interested in minimizing is in fact an average of a bunch of losses. Each Li is the loss for the ith example in the data set. So you have a data set of a bunch of images. What is the purpose of the ridge regularization? So one thing that the ridge regularization does is it prevents the parameters from growing to infinity in magnitude. In some cases, you might train a network and you might see that the parameters are escaping to infinity. If you add ridge regularization, it would prevent that. But as far as I'm aware, the effect, the importance, the purpose of ridge regularization is not really well understood. There's papers who are saying, you know, we don't actually need ridge regularization, we can just train without it. But canonically, the way, you know, people are doing it in practice, most papers use these ridge regularization techniques. Okay, so at this point, notice that there's two fundamental parameters here. The first fundamental parameter is the sample size parameter. Sample size is denoted by n above, right? How many examples do you have to train your network on? Now, in the examples that we've seen in the first lecture, in MNIST, CFAR, SVHA, and Fashion MNIST, all of these examples have something like tens of thousands of training examples, something like 50,000, right? Yes, you're minimizing the sum of the two terms. But sometimes people refer to the sum also as the loss. I guess it's a bit confusing. Maybe I should use the word objective for the sum of both terms. That's less confusing. So in this expression, we have the sample size, which is denoted by, does ridge regression help us avoid overfitting? Not really, not really. Why? Because I'll show in the in future lectures how the network is capable of overfitting despite the fact that you have rich regularization. So it does not, in fact, prevent you from overfitting. Okay. And I guess the reason is that the rich regularization is extremely small. If you use the very large reach, you might get something else. If you know something about what you expect to be a good data, say, for example, sparsity, can you use different regularization? So the answer to the sparsity is that I'm not aware of a work that demonstrated that you can optimize under a L1 constraint on the theta. There are attempts to do it in various ways to sparsify the theta, but not by imposing L1 on the theta directly and doing an optimization on that objective, if that makes sense. Does the answer make sense? Not really. Okay, so what the student is asking, can we put here, instead of L2 norm squared, can we put here L1 norm, right? My answer to this is you can, but I have not seen any paper that showed that if you minimize this objective, you get something that's better than what you would get otherwise, or that it leads to a good result of any shape or form. And there's issues associated with using L1 norm in optimization that are non-trivial. I can discuss this more in detail at the end of the lecture because this is kind of a tangential to the point of the lecture. So the second important parameter in this optimization problem is the number of parameters that you have. And so that's, I guess, denoted by P. So usually the networks that people are training in academia are of the size several tens of millions, right? Something like 10 millions, 20 millions, 30 millions. In the industry, on the other hand, the sample size and the number of parameters is significantly larger. So in the industry, you see examples where people train on tens of billions of examples and tens of billions of parameters. And what's important to remember about this optimization problem is that it's non-convex optimization, right? So in general, little is known about non-convex optimization. Now, I would like to illustrate to you how in the industry, the scaling of the problems is significantly, the scale of the problem is significantly larger. And there's a nice blog, here's the link to the blog, which discusses a project that Google AI worked on. And the project was the following. Imagine, oh, there's a question. A parameter is a single component of the theta vector. Yeah, that is correct. That is correct. So imagine you have many, many different languages on planet Earth, right? There's English, French, Dutch, etc., etc., etc. And imagine your goal as Google is to translate between every language to every language. Then this is what this paper is trying to do. It's called Exploring Massively Multilingual Massive Neural Machine Translation. So it's called machine translation, the problem, right? Translating between two languages. Now, what's interesting about the problem is that there is languages in which the number of sentences that you have of that language is large on the internet. And there are languages in which the number of sentences that you have is very small. For example, there's lots of websites that are written in the English language, but there's very few websites in comparison that are written in the Hebrew language, right? And so here you can see a curve where each dot here corresponds to a different language. And you can see how high resource languages have something like 10 to the 9 different. So in this specific case, what you can see is actually each point is not a specific language, it's a pair of languages, right? Because you're interested in translation. So each point here can be a pair of two languages, like English and French, right? So this point, for example, could correspond to English and French. And this point could correspond to English and Hebrew, right? Now, what you can see in the darker color is the translation quality of bilingual baselines. So the simplest thing you might do when facing this problem is just train a deep network that would translate every pair of languages, right? So you take every pair of languages and just train a network that translates those. And what these people found was that it's actually beneficial to train a language model which translates all languages simultaneously. Because there are languages which share in some sense different words. For example, something called Romance and Germanic are sharing some subset of the language, right? And because of that, it's beneficial to train a single language model to translate all languages simultaneously. There's a person who's, so Xin Cheng? Right,
Oh, yes.
Xin Cheng. Okay, so the y-axis here is some, for the darker color, the y-axis is the quality of translation. And for the lighter color, the y-axis is the number of training examples. And what you can see is that the more training examples you have, right, the better the translation performance in the baseline. That is exactly correct, Neo. Yes, that is exactly correct. Now, what's my point? My point is not language translation, but my point is to tell you that the networks that were trained in this project had, here you can see, 50 billion parameters, right? Imagine how many zeros exist in 50 billion. And the number of sentences on which they learn these networks is in the several billions as well. They basically scraped the whole internet and just trained the model on it. The whole internet, think about it. It's insane, right? The whole internet. And since this paper, there was another network that people at Google trained, which had trillion parameters, I think 1.6 trillion. So what if the origin of the languages are not the same? Why does it help to do it? Okay, so the question is, if the languages are not the same, why does it have to do it once for all of them? So again, their observation is purely empirical, right? They're claiming that because the languages have, some languages have some overlap, it would be beneficial to train a big network. They don't provide any explanation for why. And I agree that it's an interesting question, Amir Reza. But my point is to illustrate to you how large the problem is. This is a very high dimensional optimization problem, which is also non-convex, right? And so as a result of these very challenging optimization problems that you encounter in deep learning, people were forced to use the simplest possible algorithm one can think of. And the simplest possible algorithm that exists is gradient descent. So what does gradient descent do? Gradient descent descends in the gradient direction, right? So here's the equation for what gradient descent does. It takes the loss function, which is a scalar, right? And it calculates the derivative with respect to all the parameters at the current point theta t. So remember, the parameters are a vector of all the parameters. And so the derivative of the loss with respect to the parameters is also a vector. So if you're differentiating a scalar with respect to a vector, you get something which is a vector, right? Now, because we had the extra ridge regularization term, which is actually called weight decay in deep learning, you get this extra term, which is what happens if you derive with respect to theta, lambda over 2, theta 2 squared, right? So if you derive the ridge regularization term, you get this plus lambda theta t. And this is called weight decay. Now, so this is called a gradient, right? This is a gradient. Now, the optimization is very simple. You take theta t, which is your current set of parameters. You calculate the gradient, and you multiply the gradient by a small scalar, which is called a learning rate, alpha. And that gives you theta t minus the small learning rate times the gradient, gives you the new set of parameters, right? So the intuition is that you have this crazy landscape of some, something crazy. And at each point that you are at, you calculate the gradient and you go in the gradient direction. So this is the simplest optimization problem. And there's a little bit of extra modifications that people make in practice, which were shown to be empirically beneficial. Right, so one thing that's important to remember is all of this terminology. A lot of deep learning is, trying to remember all the fancy words that people like using. So for example, learning rate, I guess in math, you would call it the step size in optimization. Weight decay in statistics, you call it ridge regularization. Another important word is the word epoch. So epoch is one pass through your data set. So if you're doing an optimization, imagine you have a data set which has 60 billion examples, training examples. Then calculating the gradient here would be very, very time consuming, because the gradient of the loss with respect to the parameters is the sum, or the average rather, of the gradients of the individual examples, right? Now, if n is equal to 60 billion, then it would take you a long time to calculate the gradient, right? So what people are doing in practice is called stochastic gradient descent. So what does the word stochastic mean? It means that instead of calculating here the sum, or the average, I should say, the gradients with respect to theta, you just pick a random example, just one example, and you calculate the gradient for that, right? And as a result, you get an algorithm which is called stochastic gradient descent. Stochastic in the sense that the example you choose is stochastic, or in the sense that the gradient can be thought of as stochastic. Now, notice that what happens in practice, the way it's implemented, is you take your data set of examples. So let's say you have examples which are pairs of images and labels. So x1, y1, x2, y2, etc., where x's are images and y's are labels. Then in practice, what you do is you shuffle, apply permutation, and then after the shuffling, let's say you get x5, y5, x3, y3, etc. And then you just take this first pair and you use it in the first gradient step. Then you take the second pair, you use it in the second gradient step, and so on. Does this make sense?
Sorry, what you have on the bottom, that's equal to the original loss without the subscript I?
Yes, exactly. This is the loss of theta. The gradient of the loss of theta, sorry, right? Yes. Okay, so this is called stochastic gradient descent. And an epoch, important word to remember, means that you have passed once through the whole data set. And usually the way optimization works is that you take your data set, shuffle it, go through all the example once, then shuffle it again, go through all the examples again, shuffle the data set again, go through all the examples again, and so forth. So now the number of epochs is usually somewhere in the hundreds. Okay, so in the previous example, we calculated the gradient based on a single example, right? Just the ith example. But there is actually something called mini-batch gradient descent, mini-batch. what is mini batch gradient descent do? What it does is it calculates the gradient of a small number of examples in the data set. So you pick 100 examples from the data set, let's say, and you calculate the average gradient for those 100 examples. And this is what you have here at the bottom, right? So you basically take your whole data set, you shuffle the data set. So you take the data set, so x1, y1, da, 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 da. Then you apply shuffle, right? So then you obtain something shuffled. And then what you do is you take the first, let's say 100 examples, and that's your first batch. Then you take your second 100 examples, that's your second batch, and so on. So this is mini batch gradient descent. Now, an additional small modification that people use in practice is momentum. So what is momentum? Momentum is an algorithm. It has different names in optimization, but essentially what it does is it keeps track of a running average of some sort of the gradients. So if you look at the equation, it becomes very intuitive, I think. You, at each point, this is your gradient of a mini batch, right? So what this equation does is it takes the gradient of the mini batch and then it adds it on top of some running sum VT multiplied by some constant mu. So think of mu as being equal to 0.9, right? So you take your running sum at the moment, which is VT, you multiply it by 0.9, and then you add the current gradient. And essentially what this does is it keeps adding the gradients to some variable VT, which keeps all the sum of the previous gradients. Now, if you think about it, essentially what it does is it keeps updating VT with gradients, right? And gradients after many times will be multiplied by, first they would be multiplied by 0.9. Then they would be multiplied by 0.9 squared. Then they would be multiplied by 0.9 to the power of 3. So the more steps you do, the less the gradient is, what's the word? The less the gradient is impactful, right? So in the first step, the gradient is very impactful, then it would be less impactful, and so on, because it keeps getting multiplied by the scalar. And the gradient step is very simple. It's saying theta t plus 1 is theta t minus the learning rate times this running sum. Does this make sense? Yeah, the mu has to be positive and less than 1 in absolute, and has to be less than 1. Yes, that is correct. And in practice, people just set it to be 0.9. What's the weight decay for? I would say no one knows. That's my honest truth to you. I don't want to give you explanations for why people do things when I don't think there is a proper explanation. As far as I can tell, the weight decay keeps the weights from exploding to infinity. Essentially, it will become more clear in future lectures, but under certain conditions, you can show that the weights of the network will diverge to infinity, right? And if you had a small weight decay parameter, it would contain the weights from diverging. Is this a satisfactory answer, Yichao? It is. Well, okay. When iterating this algorithm, is a different mini batch being used during each new epoch? Not only in each new epoch, but also an epoch is one pass through the data set, but one pass through the data set consists of a bunch of mini batches, right? So essentially you have one epoch, which is a pass through the data set, and in a single pass through the data set, you use first the first mini batch, then the second mini batch, third mini batch, and so on. Maybe we should do a small calculation. Imagine we have a data set of size, 50,000, and we choose the mini batch. So n is equal to 50,000, and the mini batch size is of size, let's say 100. Then how many iterations do we have per epoch? How many iterations do we have per epoch? Yeah, 500. Because you have 50,000 examples and you're creating chunks, mini batches of size 100, so you have 500 chunks, right? So how many steps of gradient how many steps or updates are we going to have per epoch in this specific example? How many updates per epoch of the parameters? How many times is this last equation going to be invoked, so to speak? It's also 500, right? If you have 500 mini batches, then you have 500 gradient steps, right? Yes, so it's important to, that's why I'm creating the dictionary for you, because the most important thing, as a mathematician or people who are coming from engineering, CS, all of that, this is like trivial equations. Gradient is like nothing for a mathematician. I think you wake up and you see a gradient before you have a cup of coffee, right? But maybe like, memorizing words like epochs and weight decays, like what? Why can't we use some standard names for everything that everyone else is? Yeah. But that's why I'm emphasizing and creating, a concise list of the vocabulary that you need to know if you want to communicate successfully with people in the field. Maybe you say, I don't want to communicate successfully with people in the field. I insist on using the words I like. That's another approach. But I think that's a worse approach. So here's an example of how this is done in PyTorch. So here you can see, this is the imports of the packages. And I'm setting the batch size to be 128. Now, there is something called a transform in PyTorch. Transform is a set of operations that are applied on an image. So in this case, I'm doing two transforms. One is pad. Pad means zero padding. So if you write here pad 2, it means that you're going to pad all the images in the data set by 2 pixels on each side. So here you can see an example of a padded cat, right? Do you see the cat? It's a very nice cat. I picked the image that I like the most from the C4 data set. It was a cat. So you can see here the black pixels, right? These dark pixels are just zeros which are being padded due to this line, right? Then you have something called toTensor. What toTensor does is essentially a conversion between some data types in Python, but I don't think it's very important for you to understand what it does. So you can actually ignore this line. Just remember, you always have to do this. You always need to do toTensor. What's more important are these lines. So here I'm creating a loader. A loader is an object that allows you to iterate through a data set. So loader is an important word for you to remember. And what the loader does is it creates a data set, in this case, CIFAR10, the CIFAR10 data set. Now, this is where the data set is going to be downloaded to. And train equal to true means that we're going to be creating a loader for the train portion of the data set. You remember there is a train and there is a test portion. Now, we're also passing the transform here, which is the transform that we're going to apply to all the images, as well as the batch size. Why do we pass here the batch size? Does anyone understand? Why would you pass here the batch size? No? Gina does not. Because the loader needs to know how to package the data. Yeah, basically that. Yes, 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 yes. Yes. So basically, if you set batch size equal to 1 here, instead of this, you put 1, then you would create a loader that would give you 1 image at a time, right? But because you're doing mini batch gradient descent, you want to have more than 1 image in each iteration. That's why you need to specify the batch size. It will all become very clear in a second. So shuffle is telling you whether is allowing you to shuffle the mini batches. So basically applying a random permutation on the data. And ignore the drop loss, that's not interesting. And here I'm repeating the same thing for the test portion of CIFAR10. Now, here, what I'm doing is I'm showing you how can you iterate over the data set. So you can write for batch in train loader. So train loader is basically this thing that I showed you earlier. So it's a collection, it's giving you each time a batch from the data set. The batch is going to be a collection of images and their corresponding labels, okay? So mathematically speaking, a batch is a tuple of examples. Let's write it like this, from 1 to capital B, and their corresponding labels, right? So when I write here batch, so the batch is going to be the training images and their corresponding labels. Now, what are the labels? The yi's are just scalars, right? Just scalars that represent the class or the label of the image. If it's yi equal to 1, it means cat. Yi equal to 2 means dog, etc. The xi's are the images that you have. And so you can take this batch and you can decompose it into an image and a label. Now, what I'm doing here is I'm taking the image part and I'm printing its dimensions. And what you can see is the dimension of the image variable is 128, 3, 36, 36. So first of all, what's the 128? Why is it 128? Does anyone know? Batch size, exactly. That's the batch size. Why is it 3? RGB, that is correct, 3 channels, RGB. Why is it 36? The image size, right? And why is the image size 36 exactly and not some other number? So what's the size of an image in the CIFAR10 dataset? The size of an image is 32 by 32, right? So why do we have 36 here? Because we're doing padding. So if we're padding by 2 on each side, then it's 32 plus 2 times 2, which gives you 36, right? So the dimensions of the image make sense. Now, the next thing that's important to understand is I'm printing here the label. So I guess labels would have been a better variable name. So here you can see the labels. And you can see it's just a tensor containing a bunch of integers, right? So 3, 4, 9, da, 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 da. What's the length of this tensor of labels? How many labels do we have? 128, yes, Neo. And each one of those is just a class encoding. So for example, 3 could be a cat, right? The final thing I'm doing is I'm taking my image and I'm picking the 0th image. So 0th image means the first image. It's just that everything starts from 0 in computer science. And what I'm doing is I'm using PLT imshow, which is basically plotting the image. And then you get this beautifully looking cat right here. Isn't this cat beautiful? She's a beautiful cat. Okay, so this is the mini batching. Next, once you have the data set, you want to be able to do optimization, right? So you need to create an optimizer. So this is what this slide does. So here I'm calling optim.sgd. So optim is something I imported from PyTorch, right? And then optim.sgd is creating an optimizer. The first parameter to the optimizer is all the parameters that need to be optimized, right? So this is what I previously called theta. So it's a list of all the parameters. The next thing is the learning rate, which is usually denoted by LR, which was previously denoted by alpha, right? The next thing is the momentum, which, as I previously mentioned, it's usually 0.9. And the last thing is the weight decay. I guess for a person who's not very familiar with Python, this might look intimidating, but you can think of this as just being boxes. It's boxes with parameters in them. And so this box contains the model parameters, the learning rate, the momentum, and the weight decay. So for example, I could do optimizer. Okay, that's a good question. So this is trial and error. This is what this field is about. You take these parameters and you run them. And if you see a result that is satisfactory, then you stop. If you don't, you change one of these variables and you continue trial and error. So this is what many people are doing in big companies. SGD does stand for stochastic gradient descent, yes. So usually it is very specific. So you see, I spent a lot of trial and error for this lecture. I just sat there and I wrote alpha equal to 0.01 and it wasn't satisfactory. Then I put 0.001, wasn't satisfactory. So if I'm more serious, usually what people do is the momentum is usually set to 0.9. So that's easy to set. It is a correct statement what you're saying, Neil. Yes. The point of deep learning is trial and error. They are usually, so the momentum is usually set to 0.9, so you don't really play with it. The weight decay is usually set to 5e minus 4 or 1e minus 4, so you don't really play with it. The most important parameter is the learning rate. And usually the way you fine-tune the learning rate is either just sit there by hand and tune it, but that's very time-consuming, or you create a list of learning rates and you plot, let's say, the test accuracy as function of the learning rate. And so let's say you see that it looks like this. It means that this is the optimal learning rate. Does this make sense? So you just run a bunch of experiments over different learning rates and choose the one that leads to the best performance. Okay, now, in my description of the learning rate, I describe it as being a static value, right? So for example, in the previous slide, it's just 0.0679, which, as I mentioned, I worked really hard to find. But in reality, what people do is they actually decrease the learning rate by a factor of 10 every few tens of epochs or hundreds of epochs. So basically, the learning rate is a function that looks as follows. If this is your epoch and this is your learning rate, then initially the learning rate is high, and then you decrease it by a factor of 10, and then you decrease it by a factor of 10. Now, I can already sense someone asking, why do you do that? In life, you never want to decrease your own learning rate. That is a correct statement, yes. So I guess the question that someone wants to ask is, why do you do this in practice? Now, what would I reply to such a question? Because it was found beneficial empirically to do this in terms of performance. I guess there is some intuition to this, but it's a bit different than the momentum. Intuitively, I can show you a picture, but you shouldn't trust my pictures as being, indicative of anything. I can just show you the intuition. The intuition is that the landscape might look something like this. Let's say the landscape looks something like this, right? Then your goal is to get to the global optimum, which is this thing, right? If you use a small learning rate and you start here, you would get stuck here, right? You don't want to get stuck. So you need to have very large steps that would take you, over these mountains somewhere here, right? And then your learning rate is large, so you would hop around. And then if you decrease the learning rate, you would be able to go to the final global minimum. This is the level of understanding of people in deep learning. And as far as I'm aware, there is no good theoretical explanation for why you would do this. Why would you decrease the learning rate, etc. I mean, why would you decrease the learning rate in this specific fashion? Because there's many ways in which you could decrease the learning rate, right? If you look at classical optimization results, they would suggest you to decrease the learning rate like some function of the time, right? Something like f of t is equal to 1 over square root of t or something like that. So like there is a bunch of functions you might use as function of time for the learning rate, but this thing is what people use in practice. It seems like there is no theoretical ground for anything in this field. That is a very precise statement, but the goal of this course is to try to identify what are the theoretical claims that one can possibly make, or what are some empirical phenomena that perhaps one day we'll be able to theoretically understand. So that's precisely the goal of the course. The momentum is a bit different. The momentum, if you have a momentum, it would never get you, if you have a momentum and a small learning rate, it would never get you past this point, right? You would get stuck here if you have a small learning rate and a momentum. What the momentum does is it basically, if you have a bunch of directions, if you have a bunch of gradients that point in the same direction, then the momentum is just going to create momentum in that direction. So basically you can think of it as follows. Imagine that for some reason your gradient is distributed with a certain mean and a certain covariance, right? Let's just imagine. Then imagine if you just go in the gradient direction, then the gradient is not, let's say this is the correct direction to go all the time, this. So if the gradient is noisy, sometimes it will point here, sometimes it will point here, right? So it's essentially suboptimal in some sense, right? The gradient is not really pointing in the correct direction, it's somehow pointing slightly in a slightly noisy direction. If you use the momentum would be able to essentially get a closer direction to the mean, because you keep averaging a bunch of gradients through this variable v, and as a result you would get a less noisy estimate of the true mean. Does this make sense, or is this too poetic for you?
So was it like the momentum basically it keeps some memory of things from the past, so it decreases a lot of the noise have less and less effect over time?
Exactly, yeah.
I see. Thank you.
You can formalize it by just, writing out the equations and writing out what would happen if I just average a bunch of gradients which have a fixed mean and a certain variance to them. And you would see this, but this is not a proof, this is not a rigorous theoretical statement, it's just some intuition, right? So here's how you do this learning rate scheduler in practice. So you set a certain number of epochs, which is in my case 300, and you decide that you specify a list of epochs in which you would like to decrease your learning rate by a certain factor. So in this case, epochs divided by 3 is just 300 divided by 3, which is 100, and epochs divided by 3 multiplied by 2 is 200, right? So this is 100, 200. And then optim is a part of pytorch.lrscheduler.multistep.lr takes the optimizer that you constructed in a previous slide and takes the milestones, which is the places in which you would like to decrease your learning rate, and also takes gamma, which is the factor by which you multiply your learning rate at these milestones. So to be precise, here's the picture. This is epoch 100, this is epoch 200, this is epoch 300, this is alpha 0, let's say, which is the initial learning rate. And so this is the initial learning rate. Then at epoch 100, you're decreasing it by a factor of 10. So this would be alpha 0 divided by 10. Then it would be fixed for 100 epochs. And then at epoch 200, you decrease it by a factor of 10. And that would be alpha 0 divided by 100. Does this make sense? It does make sense. Amirez asks, if we encounter noisy samples in the first batches by using momentum, we may proceed in obtaining a bad performance because of the history, right? Yes, that is correct. That is correct. That is correct. Yet we've seen empirically that it seems like it still depends on, I mean, you know, what is luck? If one person uses momentum and trains a network successfully, then maybe that person was lucky. But if there's an industry of 20,000 researchers, PhDs, master students, you know, Google employees, Facebook employees, Twitter employees, all around the globe that use momentum 0.9 and it works, maybe there's something beyond luck. Yeah, it will make the first batch insignificant, but I think what Amireza is saying is that you might get some type of a problem if you use momentum in the first few batches, if they're very noisy. So this is the most important slide of this presentation. It shows you how does training actually work, right? So training, so the first line here specifies the device that you're training on. And so this can be either CUDA, if CUDA is available, or a CPU. So this function returns, it's a Boolean, so it returns true or false, depending on whether you're using a GPU, right? So if you're using a GPU, then the device is going to be CUDA, otherwise it's going to be CPU. The next line specifies the loss that we're going to be using. And the loss is going to be the cross entropy loss. Very simple, right? And then you have a loop over the epochs, 4 epoch in range epochs. So epoch here is going to be equal to 0, 1 to all the way to the number of epochs, which is 299. So everything is shifted by 1 just to confuse you. And then you have another loop, which is for data target in train loader, right? So what this loop does is it iterates over your training loader, which is your train data set. And so data here is the batch of images, right? And target are the labels. So the next line is moving your data and target to the device. What does that mean? It means that your data is always sitting on a CPU, whereas you want the data to be sitting on a GPU. So you need to say, move the data from the CPU to the GPU, right? If these words make no sense to you, it's okay. All you have to remember is that this is the script that you should use every time you train a network. Eventually, hopefully, you will understand what does it mean to move data from a CPU to GPU. But even if you don't, it's no biggie. So after that, we want to zero the gradient of the optimizer. So this is kind of like a clean command. It's like clean all the current gradients of the optimizer. And then we take our model and we apply it on our data, and we obtain the output, which is the logits, right? This is the output of the network. And what we do is we calculate the loss based on the logits and based on the targets, because the loss depends on the estimate of the network and also on the target, which is the ground truth label. And this gives you the loss, which is a scalar. And then what you do is you take the loss and you apply the backward function. So this is where all the magic happens. Backward is the function that calculates automatically all the gradients of your network. So it calculates using backpropagation the gradients with respect to all the parameters, biases, etc. And finally, you do an optimizer step, which is just updating your parameters using the optimizer. Now, every epoch, you need to do LR scheduler step, which would essentially, here, it would move you from, let's say, this point to the next point in the graph. Okay, so I was thinking of explaining what Adam is, but it seems like we're out of time, so I think I'll skip that. And to summarize, gradient descent, gradient descent, gradient descent, that's basically ubiquitous in training classification deep nets, and that's the most important optimizer you should focus on understanding. So that is it for today. Thank you very much for attending, and I'll stay for questions. Don't forget emailing me about the merchandise if you have ideas for merchandise. Are larger batches better or smaller batches better? So empirically, it was found. So, okay, so this is a more complicated question. So, so if you do gradient descent the way I described it, then if you use larger batch sizes, your performance, your accuracy would deteriorate. So it's better to use small batches. But if you have a very good GPU, then you want to use large batches, right? Do you agree with this statement? Because the larger the batch, the batch size, the faster you're going to train the network. If you can process at each iteration 100 images versus 1,000 images. In the case of 1,000, you would go through your data set faster, right? So yeah, you do, Amireza, you do. So on the one hand, you want to use large batches. On the other hand, I claim that large batches lead towards test accuracy. So people have developed special tricks for how to use large batches and to get good performance on test accuracy. And the trick is actually related to this plot here. So what people have found beneficial is that if you initially increment your learning rate, right? So you don't start from a large learning rate, you use an incremental approach to the learning rate, and then you use the regular learning rate scheduler, then these together with the large batch size will work well. Does any of this make sense, Xiao?
Yeah, it makes sense. Thank you.
But it's just an empirical observation. So
you're saying like all else being equal, it's better to use a smaller batch?
Yes, in terms of the performance, the test performance. You see, essentially what you're asking me is the following thing. You're saying, imagine I have on the x-axis the batch size, And on the y-axis, I have, test accuracy. Accuracy on the test data, right? So you're asking me, how does this curve look like? So the way it looks is, if your batch size is larger, your test accuracy is going to suffer, right? And so it's better to use smaller batch sizes for the test accuracy. But if you use smaller batch sizes, your training will take much longer, right? So people would prefer to use large batches. And that's why they develop tricks. Is that because it is stochastic?
So it's like a trade-off, I guess.
It is it is essentially a trade-off, because you want to use large batches because of the computational benefits, but you want to use small batches because of the test performance benefits.
And you're saying like people can get around this by
doing crazy tricks.
Yeah. Okay.
Which makes no sense to me.
But the crazy tricks are all related to learning rates?
Yeah.
Okay.
Which makes it even stranger, right?
Yeah.
So the thing is that all of these parameters are somehow intertwined with each other. So if you change the batch size, it's somehow equivalent to changing the learning rate, and it's somehow connected to changing the weight decay. So all of these things are like together somehow connected to each other, if that makes sense. Because everything here is intertwined, then it's rather complicated to understand what's happening.
I see. Thank you for the explanation.
And that kind of explains why, why a change to the learning rate might affect the usefulness of large batch training. So Jay Kang asks, is that because it is stochastic and adding white noise to the gradients compensate? I'm not sure what's the answer to that question. Is it because it's stochastic? I think it's not only that it's stochastic, it's also that it's non-convex optimization. So in convex optimization, you would use, there would be no problem with using a large batch size, because it wouldn't affect, if you have a convex function, let's say a ball, it doesn't matter, if you use a large batch size, a small batch size, you essentially will always get to the global minimum, right? But because this is a crazy landscape, then you are not necessarily going to reach to the global optimum. And so the choices like the batch size suddenly matter. Are there any other questions? So you're asking, when you say, is that because it is stochastic? When you say that, do you mean the relation between the batch size and the test accuracy? So it's an open question, basically. I don't think anyone really understands why does using a larger batch size lead to worse performance. It's an open question. People do research on this, So it's hard for me to say, why is it happening? If you answer the question of why is it happening, you can publish a paper. Does this make sense? So first of all, it's a non-trivial problem. That's what I'm saying. The second thing I want to say is that it's not really because it's, besides the fact that it's stochastic, there is also the fact that you're talking about the optimization of a non-convex function, right? So convex function is a function that looks like a ball, right? A non-convex function is a function that looks like this, for example. Right? Do you understand the difference? So if you have a convex function, for example, it doesn't really matter if you use stochastic gradient descent or gradient descent. At the end of the day, you will converge to the global optimum, right? And it doesn't matter if you use a large mini batch or small mini batch. It doesn't matter what you do, you'll get to the global optimum. But in non-convex optimization, you might get stuck, right? And perhaps the probability of you getting stuck is somehow related to the batch size.
Yeah, so I understand what you're saying. I was just wondering if there was some sort of theory there, because it seems like something that is approachable by the theory, at least in my opinion. Like, I think that I understand this idea that, these smaller batch sizes allow you to sort of somehow miss getting stuck in all these local minima that are on this landscape, right? But it seems to me like that has something to do with the order in which you're doing things and the fact that you're not doing it all at once, like you're saying. So it seems like the stochastic part of it is really the fact that you're doing it in this different order is what's allowing you to sort of fly past all these local minima.
Right. Exactly. Yeah.
So I'm wondering can you augment that with and just say, oh well, we're just going to introduce some noise,
right?
And like I've seen people do that for their I've seen in statistical learning, like the information theoretic generalization bounds. They say though SGLD, if you use noise, then your generalization is better. And so I'm just wondering if in this situation you can sort of, it seems like one of the more approachable problems. So I just thought maybe there was something there, but if you don't know of anything.
Yeah, I'm not aware of any, but the literature is so vast, right? There's infinite papers at this point. So
definitely,
if I don't know something, it doesn't mean that it does not exist. It just means that I don't know about it. I did hear about people doing what you're describing, which is adding noise to gradients. I think that it's called in physics Langevin dynamics. Do you know?
Yeah. Right? SGLD is like stochastic gradient Langevin dynamics. Yeah.
Right.
I've seen that.
Yeah. So I think people do it, but I don't know too much about it, unfortunately.
Okay. All right. No problem. Thank you.
But if you're enrolled in the course, you could do the final project on this topic if you find it interesting.
I'll think about it. If I see if I can think of something better to do, or this seems like a pretty hard one, but yeah.
Yeah, that it does sound pretty hard. Yeah. Okay.